a fair amount of memory work in this chapter as well. Okay, this is the best lesson. Pay attention here, please. Attention in the back.
I'm looking forward to this one.
This is the best lesson. Why is this the best lesson? Well, because radio amateurs nowadays do not build their own radios. They're called appliance operators by those people who build their own radios, which is a sort of, putting the guy down, eh? Most of us do this. You buy the radio, you plug it in, but you can build your own antenna, right? And most radio amateurs build their own antenna, some version of it, and put it up. And so the nice thing about it, as Bill Moss says, he said, I built that thing, I put it in the tree, and I made a radio contact with it. So you can take some pride out of what you build and use it and have fun with it, okay? So this is why this is the best lesson. It's because it teaches you how you can build your own antenna. Now there's a whole bunch of new designs out there. I'm going to show you some tonight, and we're going to talk about these things. Yeah, the pizza or planar antenna. But first of all, if we want to understand what is an antenna, you're probably going to miss me if I go over here. Okay. Well, everybody has seen a moth or a butterfly, and you see those two little antennae sticking out of the moth or the butterfly. So what do? Well, those organs on that body, they're doing a couple of things. One, they are sensing, so they're smelling through those, but also they're picking up vibrations. So they're sensing their environment, molecules and vibrations that they're picking up. And that's essentially what an antenna is do. It's a sensing device. Now on your own body, you have hairs, and if you touch a hair, even if you just touch one, you can feel it. So these are like little antennas all over your body. So if somebody touches you, you're going to feel through the hair first. That's what an antenna is doing. It's a sensing device. Okay, cats, for instance, have nice long hairs, right? They go in dark places, and those little antennae, they give them lots of information about where they are because they can't see in the dark, but they can certainly feel. So what's an antenna? It is a conductive device that converts radio frequency energy, RF, into electromagnetic waves, and electromagnetic waves into RF energy. So the first thing you need to notice here is that what's coming out of your radio is not electromagnetic waves. It's what we call RF energy. The antenna converts it into RF energy. Okay? Now, there's a lot of things here that we need to go through, definitions that you need. We need to talk about polarization. This is the direction of electrical magnetic fields. We need to talk about directivity and gain. This is how you can rob power from one place and put it in another. The length of the antenna is very important. You'll be doing calculations on that. Radiation pattern is related to gain, where the power is going. The bandwidth of an antenna, very important. What range of frequencies will it cover? And the impedance of an antenna. Also very important if you're going to match it up with your transmitter. Okay, so you'll need to know all of those definitions because guaranteed there's going to be questions on them. Now, in the 1850s, we're going to talk about really what radio is and maybe connect it with some of the other chapters. In the 1850s, people could not conceive of how it was possible, if you had an object here, how is it possible for something way over there to affect this object here without moving it physically, right? So it would either have to be a stick or something, a wind or something, that you start from there and over here that would move that object. To them, this concept that we're going to talk about was an impossibility. Nowadays, everybody, of course, accepts it. And the reason that they couldn't accept that is they didn't know about electromagnetic waves. However, motors come along, transformers come along, and you know that in a transformer you've got one coil, the primary, you got the secondary, and those two coils are not connected, right? It's inducing. One coil is inducing a current in the other coil, right? But they're not physically connected. So we're talking about induction. And that is the key to how something distant, right, which has no physical connection, can move that. That's the key. And that's essentially what radio is. It's a process of induction. And that's what your antenna is doing. It's out in the air, in the atmosphere, and a current is induced in it from a distant transmitter. Now, you know that in the transformer, you can induce quite a bit of power. But as the coil gets further and further out, of course, the power is reduced. And the power that's actually coming into your antenna is minuscule. It's so small, it's unbelievable. But the radio is designed, you've got the first thing is you get your antenna, and then you get your RF, you'll get into this, your RF amplifier, and it's sufficient, the amplification, to bring that signal, that very weak signal, up to levels that will get through the radio and produce the sound that you want to hear. So this is the basis of radio. Actually, it is induction. Okay, now next slide. Oh, you're there before me. Okay, this is the electromagnetic spectrum, and we're here, and microwaves are next. This is getting shorter and shorter frequencies, infrared and all the rest. You don't have to know these, but what you need to know is this. The shorter the wavelength, the higher the frequency, shorter wavelength, you see the frequency is higher, but also the higher the energy. The higher the energy. And that's very important, because what it means is, for instance, let's say we start out here at 1.8 megahertz, 160 meter band, but when we get to 2 meters, 10 meters, we're getting into this part, high frequency, and there's high energy in those waves, and they can be dangerous. So this is something that's going to be raised again under the section on safety. Okay, so there's no way you want to be too close to an antenna that's radiating, especially when it's in the high frequency area. The problem is that people nowadays take their cell phone going like this. Everybody has done it. They're talking with the cell phone. I don't know what it is, 900 hertz or something. So it's high frequency, right? And that energy is going right through your brain, right? From this little device. It's low power, but still there's a lot of energy in that wave. Now, if it was low frequency, it would probably just make one loop, but it's high frequency, so it's probably going about 10 times, 10, 20, 30, 40 times through your brain. Okay. We don't know yet if it's dangerous, but I don't think, based on this speech, people are going to give up their cell phones. Okay, there's two types of radiation, and people get mixed up. This is not going to be on the test, but you need to know there's two different types of radiation. We are talking about electromagnetic radiation, light, radio waves, etc. The other type of radiation is nuclear radiation. We're not talking about that. Nuclear radiation is actual particles of atoms, protons, neutrons, that are streaming through you. They're very dangerous, and they will, if you get enough of it, they will definitely kill you. We're not talking about that. We're talking about electromagnetic radiation. Okay. So the next subject is polarization. Whoa. Oh, it doesn't want to, okay, that's good. Radio waves are electromagnetic waves. 1 hertz is 1 vibration per second. Boom, 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 boom. That is a mechanical wave, right? When you get up into 1,000 hertz, it's the beginning, the very, very low end of radio waves, and it is would be very, very low frequency. Radio waves travel at the speed of light. There's going to be a question on the exam about that, and you need to know how to do conversions, because they're not just going to ask you what's the speed of radio waves in free space. They're going to say they want you to put it in kilometers. So if it was 300,000 meters per second, how many kilometers would be a second? Anybody got a good idea? How many kilometers? What would you do to convert it?
Divided by 3.6.
Knock 3 zeros off.
Just knock 3 zeros off.
Well, that'd be kilometers per second, but you want kilometers per hour probably.
Okay, oh yes, if you wanted kilometers per hour. I just wanted kilometers per second.
Oh,
Okay.
well, I his is knock 3 zeros off.
Yeah, just knock 3 zeros off, that makes it easy. Knowing how the conversions, all the conversions is very, very important, because they will always throw that curve at you that you'll have to convert it to get the right answer, okay? Okay, so if we could just scroll up a little. So there's an electrical field and a magnetic field, and this is really very simple. The electrical field is called E, the magnetic field is called H, and they're perpendicular to each other. Brent showed you this before. So the electrical field is this way. So this antenna, this would be a horizontally polarized antenna if this is coming off in that direction. Okay, there's a J-pole up there, but we can move right along. Okay, this is quite simple. The E, or electrical field, determines the polarization of the antenna. If the antenna is horizontal to the surface of the Earth, the antenna will be horizontally polarized. If the antenna is vertical to the surface of the Earth, the antenna will be vertically polarized. That's pretty well simple. Now on HF, you don't have to worry about it, because whether it's horizontal or vertical, you don't have to worry about it on HF bands, because there's a thing called Faraday rotation. You need to know that, because there was usually a question on it. What is Faraday rotation? As the wave is traveling up, it hits the ionosphere, and it's not only reflected and refracted, it's also bounced around. Magnetic fields and electric fields that change. So on HF bands, it doesn't make any difference at all. But the other night, Mike and I, you all know Mike, yes?
So in the HF bands, does it matter for the shorter range communications where you're not bouncing off
Worldwide, doesn't matter at all.
Well, I mean,
For around the world. So if I have a vertical antenna and Mike has a horizontal, and he's in China and I'm communicating with him, it's going to work.
but I mean if you are like right next to each other.
Still going to work.
Okay, so even if they're opposite polarizations,
Still
and it's
gonna
not
work.
doing any bouncing off the ionosphere, it's just
It's,
a direct.
yeah, if
still
it's
work?
ground wave, it's still going to work.
All right.
Yeah, it's still working. But Mike and I were working on the 6 meter band. Now the 6 meter band, you should know about that one, is a kind of an oddball band, because it is it HF or is it UHF, right? Well, it's oddball. It's sort of like maybe both. So we have this little net going on at 50.125 megahertz Sunday after the Twin Sioux mini net, and it's upper sideband. And what happened was, I can't hear Mike, but I can hear Brent, and I'm wondering why. Well, Mike is a vertical antenna, and Brent has a horizontal. So he is down in the mud, even though he's in the city, right? And Brent is 20 decibels over S9. So that is the reason. And if you now you go to 2 meters, and you will find that if you mix up the polarizations on 2 meters, 440, you're going to get absolutely nowhere. The signal is getting there, but because the polarization is wrong, it won't work. So you need to know that Faraday rotation. Directivity and gain. Okay. Gain is not the kind of gain that you're getting out of an electronic amplifier, the thing I'm wearing here. It's not electronic gain. In antennas, it's a totally different thing. If this is a diagram of all of the power coming out of the antenna, what actually you're doing is you're taking the energy from here and you're putting it in there. So you're stealing it from other areas and putting it in one main lobe there. That's what gain basically is. So it's, where I say it right in here, it is the increased signal in one direction at the expense of signal in other directions. That's what gain in antennas mean. The greater the directivity, the greater the gain. Now, gain is measured in decibels in relation to two possible theoretical antennas. In small print, for some reason, what is a theoretical antenna? A theoretical antenna is a mathematical formula that's got nothing to do with actual operating conditions, where you take the ground and conductivity to the ground or whatever, things in the near field, all of that is gone. Okay, and there's two types. They're going to ask you a question about these two types. There's the isotropic radiator. Now this is the theoretical antenna, and it's an antenna that radiates in all directions like a light bulb. Okay, that's what it is, an isotropic radiator. And when they compare to it, you will see this dBi, which means decibels isotropic. So the comparison is to that type of antenna. So you can't just, to claim how good your antenna is, you've got to compare it to something. So you say this antenna has 3 dB gain, dBi. So in comparison to an isotropic radiator, this antenna has 3 decibel gain. Okay? Now it's the same thing with an elementary dipole. In this case, it's dBd. Okay? And that one you will see quite often. Okay, moving along. Okay, try that control click up there, and we should get an antenna. Okay, see? Here is a 2-meter Yagi. Ooh, boy. And see what it says? 18.5 dBi, 1.5 kilowatts. 18.5 dBi. It's being compared to an isotropic radiator, okay? There it is. Okay.
Excuse me,
Yes.
that comes in the spec of that particular antenna, right?
Yeah.
Factory specs of that antenna.
Yeah, you'll get that.
Nothing that you build, nothing you do, can't compare that to any of this here, right?
Well,
Can you compare this to a DBI?
this.
Isotropic antenna, or any
Yeah,
one that
you
build?
can compare any antenna to, you could, but that's something that a technician would have to do. Like, that's way beyond all the test equipment you would need to do that.
Okay.
Yeah, but if we started manufacturing these and selling them, we would have to have them tested in comparison
To a standard,
to a standard
Yeah.
dBi, dBd, to say this is
okay.
giving you 3 dB, 2 dB, 1 dB, whatever.
But as an individual, all you care about is reception.
There you go.
Okay.
Yeah. But definitely this antenna is going to have gain. We'll get to these.
Gain in our realm is negative. Like, you don't want that.
You want gain.
You want gain.
This antenna will have gain. Gain is taking the power. If it was an isotropic radiator, right? Or let's say it's a dipole, then it's producing a big round circle of power
To get a signal from.
that is giving off its signal. Now what we want to do is we want to steal some of that power from here and we want to put it into a band like that. So that's what our gain is. It's not electronic
Right.
gain. It's a different sort of idea. Okay, decibels. Decibels are a little confusing and they're logarithmic. We're really not going to get into it. What you need to know is a doubling of power, 2 times the power equals 3 decibels. That gives you a rough guide. Now this is one thing you really need to know. The basic dipole antenna that you're putting up has 2.16 dBi gain. So it's almost a doubling of power over the isotropic regulator, okay? So, and usually there's a question on that on the exam. Length is our next subject. You remember this? Brent showed you this? Okay. And you know what everything is here. C, the speed of light, frequency. We put this as 300, and then this will turn out in megahertz. Lambda is your wavelength or band, okay? Now the important thing to realize is, it's not on the test, but the speed of light doesn't change. The speed of radio waves does not change. The frequency can change, but the speed doesn't change. If the frequency changes, the wavelength changes, but that never changes. That's always 300, okay?
So C is 300, even though it's.
Even though it's 300 million meters per second,
Yeah.
we put 300 so that when you put your megahertz in here, these things cancel out, eh?
So C is always constant.
C is always constant, yeah. That was basically Einstein, part of Einstein's theory. Okay. Okay, where are we? We're into length. Oh, yeah, there's one up. There we go. So the wavelength is essential to the length of an antenna. So we can use a modified formula to calculate the length of the antenna. You can't use that 300 formula to do it. Okay, if the length is correct for the frequency that you're transmitting on, maximum power can be transferred. This is what you call a resonant antenna. The antenna can be considered to be a resonant circuit. At the resonant frequency, the impedance is the lowest and maximum power is transferred. Okay, so I don't know if you'll be able to follow me here, but you remember your inductors and capacitors. Okay, and you remember there was two circuits. One was a series tuned circuit and a parallel circuit. The series circuit was your inductor and your capacitor, the series circuit. And basically this is what an antenna is. Okay, this is basically what the antenna is. So now you remember how it works. If you have impedance here and frequency here, when it works like this. Okay, so when you're off the frequency, impedance goes way up. When you're on the frequency, right, the frequency that the antenna is cut for, the impedance goes down, you get maximum power out of the antenna. Okay. So an antenna is essentially a series RC circuit, okay, series tuned circuit. That's how it works. Okay. Now, the antenna is actually only resonant at one frequency, but there are several ways to get around it. It's resonant at a number of bandwidth of frequencies. So you don't have to worry, you can cut one antenna and use it for a whole bunch of frequencies. Next page, please. Okay, there's your basic dipole antenna. And I'm going to come back to this a number of times. It's very easy to get confused with antennas because this entire length is a half wavelength. This length is a quarter. Okay? So you get two quarter lengths, and it's very easy to mix them up and get the wrong answers. Okay. It's really a major stumbling block when you're doing your questions. You've got to know which length you're dealing with. If you're dealing with the quarter wave, the half wave, the full wave, etc., you have to use the appropriate formula. If you use the wrong formula, you're going to get the wrong answer. Okay, and I did that a number of times in working these things out tonight for you, making calculations. I used the wrong formula and came to the wrong result, and then, you know, you got to go back at it. So with these kinds of questions on the test, you know, take your time with them and make sure you're thinking them through. Just don't plug something in and hope that it's right. Okay, now there's two sets of formulas. There's the formulas for, whoops, yes, above 30 megahertz. And the nice thing about it is it's the same as the formula for calculating the band. But we put an L there for length, not the lambda, okay? And the full wavelength in feet, if you want to do that. I don't know, do they, I'm not sure if they're using all feet or metric in the test nowadays. I think they mix it up. Okay, let's go to the, here again, you got to memorize this stuff. Next page, please. Okay, and antennas below 30 megahertz, which is the HF bands, which is mainly what we use. Here is your half wave dipole. Here is your, in meters, your half wave dipole in feet. Okay. So, typical question. A half wave antenna is approximately 65 feet, so we're going to be using that formula. Each side of center insulator. Its resonance frequency will be approximately. Okay, well, I'm giving you the answer. The half wave formula is this, 468. That's an easy one to remember, right? So I usually remember this one and this one. I know it's half wave. If I need to go up, I multiply by 2. If I need to go down, I divide it, okay? So the total length is 130 feet. 130 equals, and it comes out 3.6 megahertz, 3,600 kilohertz. So did everybody understand how I did that? Because you're going to be asked one of these questions on the test, definitely. Okay? It's very simple. It's just division. Not hard at all. But the hard part is you'll use the wrong formula and get the wrong result. You forget that you're dealing with a quarter wave section instead of a half wave, et cetera, et cetera. Okay. Nobody has any questions? We're moving along.
In the book, it says if you're below 30 megahertz, you can't use that 300.
No, you can't.
It's times 0.95 or something.
Yeah,
right?
the formula is actually adjusted, and I didn't talk about that. Let me see where I'm goofing off here. The formula is actually adjusted by two factors. There's a diameter to length ratio and an end effect or capacitance. So this is why you can't use the formula, or the formula has to be adjusted. Those two factors, the capacitance at the end of the antenna and the diameter of the wire to the length of the wire is affecting the length. So the formula is adjusted to take those characteristics, take those things into
They
consideration.
give you a theoretical number, right? That 0.95.
Yeah.
Then you have to do the percentage.
Yeah.
Out of 300.
But what amateurs do when you build an antenna, you use these numbers that we're giving you and that are in the book. You use those numbers, but you make it a little longer, you know, because you got to be careful in cutting your wire, right? You don't want to start to have to solder pieces in. And then on your insulator, so here's your insulator here. Whoops, bad insulator, and it's got a hole in it, right? And you loop your wire through, and then you coil it up, and then there it goes. Okay, so you got extra wire there, right? And then you would test it with your meter. Hopefully you get somebody to give you an analyzer, and you test it, and you see where your SWR is. I'm going to explain SWR later. And if it's too long, then you can always shorten it and just bring that wire back. It would, you know, just have more over here. So you use the formula, but you always test the antenna in real life to make sure it's getting you what you want when you build them. Okay? Now, yes, the higher the frequency, the shorter the antenna. Higher the frequency, the shorter the antenna. That's something you need to know. Okay, let's let's try it with this, because it works out very well in mechanical vibrations, and electronics work out exactly the same. Okay, going to try it with this. I'll try to hold it up. Okay, see?
Now, is this antenna in use, or do you build it for fun?
This one you built for fun. Norm built this one.
Oh,
Okay, so now watch. This is a length, right? This is a mechanical vibration, and it's vibrating. If I made this shorter, would it vibrate faster or slower? Whoops.
Faster.
Absolutely correct. Okay? See? It's vibrating faster. Shorter, faster. Shorter, faster. Okay, and it's the same thing with antennas. The higher the frequency, the shorter the antenna. And they usually have a question on that on the question bank. Okay, here's something I threw in, the demonstration with the wire, but also to calculate the half wavelength of a person measuring 166 centimeters or 1.6 meters. How would you go about doing that? The half wavelength of a person, 1.6 meters. Well, let's assume that the person is an antenna 1.6 meters long, a vertical antenna. What are you going to do? We're going to assume it's in the over 30 megahertz. So, and it's half wave. We could have taken a quarter wave. So our formula is, what was it? It's 300 equals length equal over megahertz. So we know the length, the fellow is 1.66 meters, right? These are interchangeable. So we want to figure out the frequency. But we said it's half wave, so we can't use the 300. If it's half wave, we have to cut it in half. Or a quarter wave, we'd have to cut it again. So this is 150. We want the half wavelength of the person, okay? So can somebody do that? 150 divided by 1.66. Anybody got a calculator? $90. That's 90 megahertz, right? 90 megahertz. Okay, now, don't get your formulas mixed up. 90 megahertz, what band is that? What formula are you going to use? What formula are you going to use to figure out the band? The wave band, lambda.
300.
300 divided by 90.
90, yeah.
300 divided by 90. Anybody got that? What's 300 divided by 90?
3.33.
The 3 meter band. Okay. So why am I giving you this example? The human body is just like anything that's in the environment. Absolutely everything in the environment is absorbing radio frequencies. Everything, including your body. Every piece of metal, everything is absorbing it. So my body is 1.66 meters, and it is absorbing the frequency of 90 megahertz that's going through my body. I am picking up FM radio with my body. Now, if I got close to this station, being my size, right? I got close to that transmitter, 90 megahertz, that power would want to couple with me, right? And it would be dangerous. They're very dangerous for my body. Radio frequencies are dangerous anyway, but that one would be especially dangerous for me because the length of my body is acting as an antenna. Okay? Okay, an antenna is resonant at 5 megahertz. 5 megahertz. To make it useful in the 80 meter band, what would you need to do? Lengthen it, center feed it with TV ribbon, shorten it, ground one in. So 5 megahertz, where is the 5 megahertz? 5 megahertz, yes. The 60 meter band, we want to go to the 80 meter band, right? So what are we going to do? Any ideas? We're going to do that antenna. It's working at 5 megahertz, but it's not useful to know because it's too high a frequency. We want to make it a lower frequency. To make it a lower frequency, we
Make it longer.
make it longer. Exactly right. Okay, we're going to make it longer. Yeah. Oh. There was a thing. Let's not skip those things. What is this? I have no idea. Control click. Whoa. Went away. Control click. Whoa. Ah, okay. Keep going up. Scroll, 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 scroll. Keep going. Okay, stop, 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 stop. Okay. These are all of our bands. And this is what you need to know. Here's, for instance, our 40 meter band, 30 meter band, 20 meter band, 17 meter band, 15 meter band. You got to know what these things are. When you know what those bands are, you won't have to do the 300 over megahertz to get the band. You'll know automatically when you see it what the band is. Okay, 12 meter band, et cetera, et cetera. This tells you, you know, basic and 5 words a minute, basic and honors, basic and advanced, what the privileges are, et cetera. I think Brent brought this up before, and this gives you the maximum bandwidth that you can transmit at. But basically, you're going to have to know these things. You're going to have to know where the band starts, where the band ends, and the bandwidth. There's a lot of memory work there.
So you really telling me you have to memorize every one of them?
Pretty well. They're going to ask you a question. They may only ask you 2 questions, you know, but
I'm not going to know which one they are.
yeah.
And another kind of off topic a little bit, but
Okay.
the up to the 15 band, whatever you call it.
Okay, this number 15
meter band.
is the, that is actually the 10 meter band there. I don't know what that number is.
Okay, right.
Just the 15th.
Can't really see that, but anyway, the qualification is the thing on the right-hand side.
Yes.
The,
Whoa. Yes?
that means that and a guy that only makes 70 on the test cannot get in those bands. Is that what that's saying?
Yeah, to operate on that band, you need
Basic plus 5
basic,
words per minute and or basic with honors. Is that right?
yeah, you would need the basic, which would be the 70%, and the 5 word a minute code,
Yeah.
or the basic with honors, or the basic and advanced.
That's right. And normally where would guys like us operate with bands?
Normally, guys like us are in the HF bands. We're in the HF bands, but we do go into these bands because you remember these bands don't travel far. These bands travel the 2 meters, 440, 220. They travel in a direct line. They don't skip.
They don't.
So
Is it too-
we're going to use those for local communication. We're going to use repeaters to jump around on them, but we're
They don't skip because the frequencies are too high. They go
too high. They go straight through.
Okay.
Yeah, they tend to go either straight up or straight through. But if you only get to 70%, then you're going to be down a little. You're going to be, yeah, you're going to be right here and up if you only get to
And who are
70%.
talking those type of frequencies?
A lot of people are, Twin-Sioux Mini-Net is on there, and also with digital technology, we connect them through the internet, and we can talk around the world on those, even though we don't have it. But you still cannot go into HF bands if you only make 70%. So, as I said before, what you do when you get about 3/4 of the way through the book, you start hitting those tests on the Industry Canada site. Take them over and over and over again. Find out where your problems are, what you don't know, fix that problem, and keep going. And most, I know it sounds daunting, but Ken is here. You could talk to Ken. Norm is here, and people who have passed the exam before. Ernie's passed. You know, Mike has passed. You could ask them questions. How hard really was it? And it's really not that hard. It's a lot of memory work. It's more dedication than it is anything else. Okay, radiation patterns, if we can go back. What's the time? Oh, we got about 15 minutes, eh? Okay, next one up, radiation patterns. Okay, this is the radiation pattern of a standard dipole antenna looking from the top. So it's got two lobes out the side. So if this is north-south, then your lobes are coming out east-west. Okay? That's basically it. If you're looking at it from the end, it's just a big donut. But this is, again, theoretical because it's going to depend on the ground. It's going to depend on, you know, your eaves trough, your neighbor's fence, if it's metal. All the metal in the area is going to be affecting it. So it's theoretical. And you really don't need to know that. If you're making a contact, you're making a contact, you know. Okay. Next page. Okay. Some of the waves go directly into space, the direct wave, and some of them bounce here and are reflected here, okay? So you get a reflected wave. Now, this does not exist. What's down here does not exist. It's virtual. They'll tell you that in the book. But it's as if there was, the antenna was doubled and it's coming out at that angle. The angle of the reflected ray and the direct ray is dependent on the height of the antenna above the ground. The higher the antenna, the lower the angle of radiation. Why is the angle of radiation important? Mike is sitting there with a very good vertical antenna that has a low angle of radiation. You're going to see in a minute, I do not have that. So Mike should be able to work distant DX or distant transmission. He should be better than me because of his antenna. Okay, here's the surface of the Earth. Okay, here's our ionosphere. Okay, here's my transmitter. Here's somebody else over here. I want to try and get there. And just to carry off on what Jerry was saying, okay, 2-meter radio, it's going to go straight up, and it's going to go straight along the surface of the Earth, and that's it. It's not going anywhere. So it's local communication. But now we're into HF, but I haven't got a good angle of radiation. So this is what's going to happen. Okay? Now, my poor fellow's in a skips over there, so I didn't draw the drawing right. Okay, so you're getting the skip. It's bouncing off the ionosphere a number of times. Okay, but if I could lower that radiation, as a vertical antenna does, as Mike has at his house, was the R6? R7. 7 band. Oh, boy. Okay, the angle of radiation is going to be lower. Okay, now watch what happens. See? It's lower, and therefore you're getting greater skip. Okay, so this is why you want low angle of radiation. Now, it's pretty hard to get. A vertical gets it for you, but a dipole, it's pretty hard to get. Yes?
Is it true that every time the signal reflects or refracts, it loses some energy?
Yeah, it loses energy every time.
You want less skips.
You would want less skips. You want lower angle of radiation.
Right. Okay.
But verticals are good, but verticals have the other problem. We'll get into vertical antennas. They have their own problems as well. But a low angle of radiation is a good feature if you could get it. We're going to get back to some of these characteristics. We've got to talk about bandwidth now. The next slide. Bandwidth. An antenna, you don't have to, when you first start thinking about antennas, you say, well, it's resonant on that frequency. I have to cut an antenna for every frequency that I want. You don't, because an antenna has a thing called bandwidth. And the bandwidth is the range here of frequencies over which the SWR, we're going to explain that later, is 2 to 1. Okay? SWR stands for standing wave ratio. Okay, so you cut an antenna for 3.6 megahertz, it's going to work 300 kilohertz wide. it's going to give you a whole band of frequencies that you can operate on. Okay? So that's how that works. Now, what are the factors that affect the bandwidth? How can you have an antenna that has greater bandwidth? Well, one of the ways you can do it is you can increase the diameter of the radiators that you're using. If the radiator is bigger, you've got greater bandwidth. The antenna will have greater bandwidth. Some antennas have great bandwidth and some don't. The dipole antenna tends to have about 350 kilohertz of bandwidth. Okay, so if you're really stuck on bandwidth and you wanted to do it, and this is an example so you remember it, the greater the diameter of the radiator, the greater the bandwidth. So what some people have done, you know those useless CDs that you're going to throw out? You keep them. There they are there, okay? And this is going to be 1/4 of the antenna. Your insulator is going to be here. And you're going to have another wire here, this wire, and you're going to put holes in this. How many we want? And you're going to go through. Okay, this is a pretty bad drawing, but I think you're going to get the idea. So you used many wires instead of one. And this will increase your bandwidth. Now you have to have that same over here. The problem with this is it's going to be heavy. It's going to sag. But some people have made this because they're fussy about bandwidth. I'm going to explain later on that you don't really need to be that fussy about bandwidth. Yes, sorry.
Could you just use a large diameter pipe?
Yes, you can. But keep in mind you got to support all this stuff. And so, you know, look at the lengths that you're going to use. You need, well, the G5RV is 51 foot on the side. See, so you got to support that 51 feet, 30 foot up in the air. So now this is starting to become a mechanical nightmare. That's why most of us just use a single piece of wire, right? And it works well enough. Okay. Yeah, and so you need to know that the dipole typically has 300 kilohertz bandwidth. Then on 20 meters, oh, we goofed here. We goofed here. Okay, where is that other chart? Let's go. Yeah, okay. So 80 meter band, look at how big the band is. It's 3.5 to 4. It's 800 kilohertz wide. But the 20 meter band is 14 to 14.35. So you cut an antenna for the middle of that band, and that antenna is going to cover the entire band. But you cut an antenna for the middle of this band, ain't going to work. You're not going to have the bandwidth on that particular band. On this band, you're going to have to make a decision whether you want to go here or you want to go there. Okay. So, am I at fault? Yeah. But there's another way of getting around this problem with bandwidth. Antenna tuner. And as Bob Heath was saying last time, it's not an antenna tuner, it's a matching network. Well, that went out with, you know, that's old hat. We call them antenna tuners. So what does the antenna tuner do? It inserts inductance and capacitance in there to obtain a match between the transceiver and the transmission line. However, when you're using the antenna tuner, and you're not using the antenna isn't resonant, you're in a portion of the antenna where it's not resonant in terms of frequency, then your SWR is going to go up. I'll explain that, standing wave ratio, and you're going to lose power. It's not going to be as efficient as if it was, but it doesn't make a lot of difference. It's still going to work. Okay, what's the time? I think we should take our break now, 5 minutes early. How does that sound? Time for break? Coffee? Unless you're dying to carry on.
Can you go, I've never seen what you just did here.
This? No, it's 1930s technology.
So so you would, if that was like a G5RV, I would use a disc and run 5 leads.
You have 5 wires through it, or whatever.
And 5 the other way.
Yeah,
Just to get.
bandwidth. You would probably do that on the 80 meter band if you wanted just the 80 meter.
No, I understand that.
Get you the whole band.
This
Yeah. It's, the only reason I use that is to get across the idea that bandwidth is dependent on the diameter
Yeah, but would
of
they
the
be-
radiators.
Would they be tied at the other end?
Oh yeah, they're all tied together. Yeah.
Okay.
They're all tied together. But the problem is, you know, this is going to jiggle in the wind. It's going to be heavy.
And it's a sail.
Yeah, it's a sail. I wouldn't build it. Personally, I wouldn't do it. But just to get the idea across, the bigger the elements, the bigger the bandwidth. That's the idea I want to get across. Yes.
So, for a vertical antenna, which we haven't really talked
Yes.
into too deep yet, would that big pipe be a good option? Just a
Yes.
big vertical pipe
Yes.
sticking way up in the air.
Yeah, you know, you can, vertical antennas, we're going to get into them, are usually quarter wave. Now, you see, if you wanted to do the 80-meter band, that's pretty high.
Use a flagpole.
Yeah, you can use a flagpole. And usually what they do, we'll talk about this later, I think Brent talked about it too. Two things you can do with the vertical, because if somebody can figure out what is, okay, what's the formula? It's 143, 143, divide that by 2, that's your quarter wave in meters, 71.5, and you want the, let's say you wanted the 40-meter band divided by 7 is equal to, that's not bad, 10 meters high. That's 30 foot high. Would get you the, see, but you're not going to get the 80-meter band or the 160. See, but you can, with 10 meters, it's 30 feet. But what they do, 30 feet, you're going to get a lot of wind, too. So there's two things you can do. This is going to be insulated from ground, of course. You could put a coil here and take different points off where you can match it to your, match it. You can also put up here a thing called a capacitance hat, right? And what that extra capacitance does is it will allow you to get other frequencies, which the antenna is not resonant for, but you will see that on antennas sometimes. Okay, so those are two little tricks. Peter, you're not going to see Peter this time around, but Peter has an antenna. One of our V380Q has an antenna at camp. I think he's about 40 feet high with that. And he has a capacitance hat, and we call this a loading coil. And he works the 160 meter band, 1.8 megahertz. He's working in Morse code contests. Okay, let's have a break. I'm thirsty.